Now, here is a flow equation. Has anybody seen this flow equation before? V equals IR. Anyone seen this one before? Okay, hopefully you have. This is a flow equation. We're talking about electrical flow. V is the pressure. I is the flow. R is the resistance, which is basically the constant. There is a similar flow equation for fluids. And the flow equation for fluids looks like this. P, Q is the flow. Let me just put some of this stuff down. P is pressure. Q is flow. And K is a constant. So, as you can see, there's an electrical flow equation, and the electrical flow equation states that flow equals pressure times constant. There's a fluid flow equation. The fluid flow equation states that flow equals the square root of pressure times a constant. So the difference between the electrical flow equation and the fluid flow equation is that the fluid flow equation takes the square root of the pressure. Now, using the electrical flow equation, if I need to know the flow in a piece of wire, then what I do is, and all I have is a voltmeter, then what I do is I measure the voltage across a resistor. And the voltage across the resistor lets me know what the flow is, because there is an equation. And the equation is that I equals V over R. If I know what the resistor is, I know what the voltage across the resistor is, I know what the flow is, because I equals V over R. With fluids, we do the same thing. We put a resistor of some sort in the pipe. We then measure the pressure across that resistor. If we measure the pressure across the resistor, we can find the flow, because we know, just like V equals IR and I equals V over R, we know that there's an equation, and the equation is that flow equals square root of pressure times a constant, and that constant is the constant for the resistor that we put in. So that is one of our main ways of measuring flow. We actually measure pressure across some kind of resistor. The first type of resistor we're going to look at is basically, it's an orifice plate. This is a plate with a hole in it. So we have an orifice plate. It's quite a very simple, very low-tech solution. It's a metal plate with a hole in it. Now we're starting to look at flow meters. When we look at flow meters, I need to ask a few questions each time. Now when I ask the questions, you'll see there's a little tick and a little cross on the top of your screens. If, so there's a little tick. A little tick looks like it's a little green tick, and there's a red cross. Okay, when I ask these questions, if you can give me a tick or a cross if you think it'll work. Right, there are 3 types of orifice plates. Now, with an orifice plate flow meter, it's basically a metal plate with a hole in it, and the fluid goes through it, and we measure the pressure either side. Now, will this work for gases? Well, we've got a split decision there. In actual fact, it will work for gases. It will provide a resistor for the gases. So it will work for gases. Now, will it work for water? Yep, it'll work just fine for water. Will it work for oil? Yep, it's good for oil as well. Will it work for water with air bubbles in it? And I'm looking at my first one here. Oh no, air bubbles are not going to do good stuff in this. What air bubbles are going to do is air bubbles are going to build up. In the air bubbly sort of way they do, air bubbles will build up just before the orifice plate until the air bubble gets big. And then the air bubble gets bigger. And then what happens is the air bubble blocks the pipe. No flow. And then what happens is the air bubble gets pushed through the hole. Bloop. Like that. Now when the air bubble gets pushed through the hole, that's very unpleasant, because not only does the flow suddenly resume as the air bubble goes through, the next air bubble starts building up on the other side. Now what we have is we go from zero flow to maximum flow, and then back to zero flow, and then back to maximum flow. Now, this is a process that we call slug flow. Another name you may have heard for is water hammer, and it's going bang, 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 bang. All the pipes are water hammering. That is a very, very bad thing. So, if we have liquid with gases in it, then what we would tend to use is, instead of using a concentric orifice plate, concentric means the centers are the same. If we have liquid with gases in it, we use an eccentric orifice plate, and we use it with the hole at the top so that it looks like, and then the little metal tag is underneath. Okay, so instead of if we have liquid with gases in, we use an eccentric orifice plate. Now, will this orifice plate work if we have liquid with solids in it? What do you reckon for liquids with solids? No, you're absolutely right. Liquids with solids are going to do bad things. And what I'm principally thinking here of is mineral sands and sewage. Sewage is essentially liquid with solids in it. Liquids with solids will block up on a concentric orifice plate. They will also block up in an eccentric orifice plate. If you have liquids with solids, you need to use a segmental orifice plate. Okay, so liquids with gases, we use eccentric. Liquids with solids, we use segmental. Now, there's a couple of things you should know about orifice plates. The first thing is the reason why there's a little tag on the end of them. There's three reasons why there's a little tag on the end of them. The first reason is it gives you a convenient place to write down the resistance value of that orifice plate, what's called its kV. The second reason is because the little tag is on the opposite side of the hole. So the little tag lets you know where the hole is. If the little tag is pointing downwards, the hole's at the top of the pipe. If the little tag's pointing upwards, the hole's at the bottom of the pipe. So, the little tag lets you know. The third reason for the little tag, of course, is so that it can catch you as you're crawling over the pipework. And it really hurts. That's why you actually quite often see orifice plates without the little tag. Because generally speaking, once somebody's caught their knee on one of these things, they kick the crap out of it, and the little tag gets broken off. Then sometimes, if they're conscientious, they weld it back on again. Now, a big problem we get with all of the types of flow meter that measure pressure, whether it's an orifice plate or one of the many other types, is that, oh, that's wrong, is that in actual fact what we're doing is we're measuring differential pressure. We have a differential pressure sensor. That differential pressure sensor is usually mounted some distance away from the actual pipe, which means that it's piped to the pipe using little thin pipes. These little thin pipes are called impulse pipes. Our main call out for DP type flow meters is not that the DP's gone wrong, or even that the orifice plate's blocked up, or many other things. Our main call out for DP, differential pressure type flow meters, is that the impulse pipes have got air or crud in them. And our main call out is we go in and we bleed the air out of them, or we go in and we blow high pressure air through them or high pressure water through them to clean the crud out. That's a problem we get with this type of system. That's something to bear in mind if you've got them. Okay, the next type of flow meter we'll look at uses what's called Bernoulli's principle. Bernoulli's principle states that if you make a fluid flow faster, it exerts less pressure. Bernoulli's principle is used in all sorts of things. In one place you probably see it used is in aircraft wings. With an aircraft wing, the air flows over the top and the air flows under the bottom. The air going over the top has got further to go. So because it's got further to go, it travels faster. Because it travels faster, you end up with a low pressure at the top and a high pressure at the bottom. The upshot of all of this is the wing gets lifted. It creates lift. That's one of the consequences of Bernoulli's effect. Basically, Bernoulli's effect says if you make a fluid travel faster, you get low pressure. We use this effect in lots of machines. We make a thing called a venturi. If you make a venturi piece of pipe and you blow fluid through a venturi, as the fluid speeds up to get through the narrower piece of pipe, the pressure drops. What that means is we end up with vacuum, suction, at the middle bit of the pipe there. Now we can use that to do all sorts of things. If we can pull a pipe off of that, if we put that pipe in, say, a can of paint, anybody know what that is? A venturi with a can of paint? What do you call that? A spray gun. You're right. Another thing we can do with that is if we put, instead of put it into a can of paint, if we put it into a can full of petrol, so that it sucks petrol in. Now, many of you may only have ever seen fuel injection, but if a venturi, yeah, it's a flamethrower. It's actually a carburetor, but it's also a flamethrower, and it's also a jet engine. All of them work on the same principle. A venturi, sucking fuel in, and if you have some sort of ignition on the back, then you have a flamethrower or a jet engine. We're going to use, oh, there's pictures of orifice plates. Oops, go back. We're going to use this Venturi principle, Bernoulli's principle, to measure the flow in a pipe. And we do that by having a piece of pipe which is shaped like a venturi. And then in the middle bit just here, we have suction. If we compare the pressure at the middle bit with the pressure at the beginning bit, using a pressure sensor, then we know how much flow there is, because the more flow there is, the more suction there is in the middle. So by comparing the pressure using a differential pressure sensor, we know what the flow is. Now, remember the ticks and crosses? Will this work for gases? Yes, it will. It will work just fine for gases. Will it work for water? It will work for water, because water's a nice clean water, I should say. It will work. Now, will it work for oil? Yep, it's good for oil. Will it work for water with air bubbles in it? And the answer is it will work for a little while. In very short order, as you've probably already predicted, the air bubbles get into all of these little spaces here, and the air bubbles get into these pipes, and then it stops working. Will it work for water with crud in it? Once again, it will work for a little while before all of these little pipes are blocked up with crud, and then it stops working. Oh, talking's on fast and squeak. I'm just going to go offline for a moment and try and sort this talking out. Hello, can you hear me? Do I still sound like I'm on helium? Is it all helium-y or okay? Oh, good. Right. Okay. So, Venturi tube, great system. They're quite expensive. The problem with them is that they're quite bulky and they're quite difficult to install because they're quite a big bulk. Venturi tubes, though, on the whole, are pretty good flow meters. They're much... Oh, come back. They're much better than an orifice plate. An orifice plate has got the aerodynamics of a caravan. It really, really messes the flow up, and it really reduces the flow. Whereas the Venturi tube doesn't reduce the flow because it doesn't mess up the flow characteristics. The next one is a thing called a flow nozzle. Now, let me just colour the actual flow nozzle bit in. Do they wear? Venturi tubes don't wear. Orifice plates, yes, they do wear. Oh, yes, they do wear. The nice thing about an orifice plate is it's really easy to replace it, because all you do is you undo the bolts on the flange, it drops out, and you shove a new one in. But yes, they do wear, and if you're talking mineral sands, they wear pretty quickly. Now, what they attempted to do is they attempted to make the best of both worlds by building a thing called the flow nozzle. I just shade in the actual flow nozzle part. The flow nozzle is supposed to have the aerodynamic characteristics of a Venturi while being as cheap and cheerful as an orifice plate. Now, when you try and do the best of both worlds, what you often end up with is the worst of both. And that's exactly what you end up with a flow nozzle. Because you end up with something that still wears out, just like an orifice plate wears out, still interrupts the flow, not as much as an orifice plate, but the worst thing about the flow nozzle was the way they tended to be, or the way they tend to be installed. See, this is showing a flow nozzle using a thing called a fillet. This is a fillet. And what you're supposed to do is you're supposed to have a fillet which bridges the gap between the two flanges. That's how you're supposed to install it. That's not how anybody actually installs them. The way they actually install them is just the same way as they install an orifice plate. They just shove it between two flanges and do the bolts up. Now here's the problem. If it's just shoved between two flanges and the bolts are done up, when an orifice plate wears, you undo the bolts and the orifice plate falls out. When a flow nozzle wears, you undo the bolts and it doesn't fall out because it gets stuck in the pipe. Now you've got a big problem. The stupid flow nozzle won't fall out. Now what you have to do is you have to get hydraulic presses and put hydraulic presses either side of your pipe. And you have to push your pipe down. It's called springing the pipes. And you push your pipes down or you push your pipes up using hydraulic presses, and you hope that the flow nozzle falls out before the pipe cracks. And so it's one of these things. In theory, it should be the best of both worlds. In practice, it's a mess. The next type of flow tubes are pitot tubes and anubars. Now, you've probably seen pitot tubes before, and the place you would have seen them is on the outside of an aeroplane. I'll just get a copy of one. Copy. Paste. So, this is a pitot tube on an aeroplane. And the idea is that the air pushes into the tube. The air pushes inside that tube. The faster the airflow or the faster the fluid flow, the more pressure there is. We compare that airflow with, there's another orifice on the pitot tube. On this pitot tube, the second orifice is there. On this pitot tube, the second orifice is just there. Okay, so we compare the airflow being pushed into the pipe with the airflow going past the pipe, and the faster the flow, well, the more the pressure difference, the faster the flow. So a pitot tube is used to measure velocity, and from that velocity we get flow. On aeroplanes, it gives you air velocity, or, yeah, that's what it's called, isn't it? No. Airspeed. Now, the problem with the pitot tube is that it only measures velocity at one single point in the pipe, which is fine if you've got fully turbulent flow, but completely messed up if you don't. To try and get round this problem, they also make things called anubars. And an anubar, this is an anubar over here, this is an anubar. What an anubar does is it's like a whole bunch of little pitot tubes, loads of holes, and it averages out the velocity across the pipe. So you have pitot tubes and anubars. Once again, they're still measuring pressure, and they're using pressure to calculate velocity, and then we use velocity to calculate flow. When we're using pressure to calculate velocity and velocity to calculate flow, differential pressure times flow type flow meters, there is a square root relationship between the flow and the pressure. So the relationship is flow Q equals square root of pressure times a constant. When we set up our flow meter, when we're doing the setup, there's a value which is normally called linearization. Linearization. And when we're setting up a pressure sensor to be a flow meter, we need to select square root, linearization. If we select linear linearization, we'll get the wrong values. Now, here's a trap. When you're calibrating a flow meter, you generally calibrate it at 2 points. You calibrate it at the 0 point, and you calibrate it at the maximum point. So what you do is you tell it that you've got these two values, the lower range value and the upper range value. When we calibrate in a flow meter, we generally say, all right, I want, in this case, my lower range value is 0. So 0 is my lower range value. My upper range value on this graph is 10. This graph is showing the two possible characteristics. I've got the linear thing here. This is what would result I would get if I'd chosen square root linearization. If I'd made a mistake and mistakenly chosen linear linearization, this is how the flow meter responds, the bottom curve. Now, unfortunately, if I do what's called two-point calibration, which is lower range value and upper range value, then if you look at those 2 points, both of these graphs are the same. What this means is that at install, if I incorrectly choose the wrong type of linearization, I won't realize. And it might not be until years down the line that someone realizes that when my flow meter is saying that it's 12 milliamps, for instance, 12 milliamps is mid-flow, my flow meter, when it's giving out 12 milliamps, will be saying that it's 5 liters a minute. But the real flow will correspond to the other line. So the real flow will actually be more like 7 liters a minute. And it might not be until a couple of years down the line, one of the operators says there's something very wrong with this flow meter, that anybody realizes that the install engineer, instead of selecting square root, selected linear. So that's a little bit of a trap for young players.